Hi, I'm Chris Porter. My collaborators and I are presenting Decker, attack surface reduction via on-demand code mapping. Modern applications are bloated with unused functionality. Code reuse attacks continue to leverage all of this extra code for malicious ends. Recent code reduction techniques are typically either sound but conservative or aggressive but unsound, which can lead to crashes. We take a constructive approach to attack surface reduction called Decker that tries to span this gap. This is a deck. And in our analogy, this is an example program standing on the deck. All code on the deck is always executable and available for attack. Now consider the associated pseudocode for this example call graph. Function main may invoke foo and bar. The idea of Decker is to construct decks only for code that is actively being used. When this program begins executing, only function main is active, so Decker constructs a deck solely for main. If execution reaches the call site of foo, then we create a deck for foo, which maps its code as executable. The program can continue normally to foo, and when foo returns, the deck is torn down. A normal program keeps all of its code always active, and attackers combine parts to construct code reuse attacks. The strength of Decker lies in its ability to remove large sections of the program that are not in use, thwarting such attacks. Please come to our talk for more details. We'll show how to use static compiler and dynamic runtime techniques to achieve this. Our technique is sound. We have several case studies, including for Nginx, showing multi-platform support, low overhead, and real-world attack breaking scenarios. Thank you.
We are Shaohua and Zhendong from ETH Zurich. We present a new way of finding unstable code via compiler-driven differential testing. Unstable code refers to source code that contains undefined behaviors. For example, in this code, 1x equals to integer max, x plus 1 overflows to integer min, and b less than x consequently. However, integer overflow is undefined behavior. Compilers such as GCC may choose to remove the if branch, and thus the resulting binary will always return to. Other compilers such as LVM will choose to keep it, and thus the resulting foo function will return 1 when calling it with integer max. You may observe that these two functions returns differently, even though they are come from the same source code. Our idea to detect unstable code is based on this fact. Given a source code, we compile it with different compilers and different optimizers, and to get a set of executables, and then feed the same input to these executables to get a set of outputs, and then we examine whether or not these outputs are the same. Any discrepancies imply the existence of undefined behavior. We call our approach compiler-driven differential testing, or COMDIF for short. Together with ASPLOS, we have detected over 70 bugs in many real-world applications. If you are interested in more details, you're welcome to session 7B. Thank you.
Current hardware is great at isolating large things, like operating systems, but bad at isolating small things, like functions and libraries. And this limits how we build applications. For example, developers today write their applications to run in a single address space. Because high hardware overheads make breaking applications into different parts impractical. Thus, any bug often compromises an entire application. Also, developers are increasingly relying on deployment technologies like microservices and Lambda, where current hardware imposes excessive overheads and complexity. To overcome these limitations, developers are increasingly turning to software-based isolation in the form of WebAssembly. Unfortunately, software-based isolation also has a lot of limitations, such as performance overheads and scaling limits, that make it less than ideal. To overcome these limitations, we developed HFI. HFI is a simple hardware extension that offers the best features of software and hardware-based isolation. Like software, it offers low overheads for creating and switching contexts and sharing memory. And, as hardware, it also offers bare metal performance, secure high-assurance isolation, and removes the scaling limits imposed by WebAssembly. HFI provides hardware assistance that makes WebAssembly faster, safer, and more scalable. It can also isolate unmodified native binaries. It does all this with minimal additional hardware and minor changes to existing processors, making it easy to adopt. To find out more, please check out our paper and come to our talk at ASPLOS 2023. Thanks.
Hi, my name is Christopher, and I'm going to be talking about protecting systems by protecting system calls. System calls are an API interface that form a bridge between applications and the host operating system. All applications use these services in one way or another. Unfortunately, code can still contain vulnerabilities an attacker can use to leverage this very same bridge. System calls can then be used to achieve harmful objectives such as arbitrary code execution or privilege escalation. While attacks can vary in how they are carried out, many attacks converge to reach and abuse one or more system calls to complete their attack. With this insight, instead of protecting at earlier attack steps, why not protect modern-day systems by protecting what attackers want most, system calls? The key idea behind our work is observing attacker abuse of system calls and shoring up defenses. We introduce a new concept called system call integrity that's comprised of 3 contexts, all concerned with ensuring legitimate system call usage. For example, for the system call below, exec v, system call integrity enforces that it is reached legitimately with an expected control flow, it is invoked correctly, and that none of its arguments are corrupted. We implemented Bastion to apply system call integrity and protect real-world applications. Bastion analyzes program using a compiler framework and enforces system call integrity during runtime using our runtime monitor. What sets Bastion apart from most defenses and allows it to achieve low overhead is that system call integrity only needs to perform context integrity checks when a system call is invoked rather than performing checks along the way. To learn more about our work, please attend our talk in the Software Security and Privacy session at ASPLOS on Wednesday, March 29th at 10:20 a.m. See you there!
I'm Karthik, and I'll be giving you a brief tour of our work on characterizing and optimizing end-to-end systems for private inference. We are interested in two-party neural network inference in which a client has some data and the server has trained and deployed a neural network that the client would like to query. The goal of two-party private inference is to perform this prediction directly on encrypted data, thus preserving the privacy of both parties. And this is achieved by using a combination of cryptographic primitives. Homomorphic encryption and secret sharing are used to privately compute linear layers, while garbled circuits and oblivious transfer are used to privately compute the ReLU activation function. In this work, we analyze state-of-the-art private inference protocols and identify 3 bottlenecks that prevent them from scaling. First, a large storage burden on the client. Second, high compute latencies on the server. And third, an increase and imbalance in the amount of data transmitted between the parties. We propose optimizations to mitigate each bottleneck. We introduce a new protocol that moves the heavy storage cost to the server. We identify independence in the server's compute stack and parallelize this computation. And finally, we allocate both upload and download bandwidth to minimize communication latency. These optimizations provide an end-to-end private inference speedup of 1.8 and increased maximal sustainable throughput by a factor of 2.24. To learn more about our work, please
attend our talk on Wednesday during session 7B.
Hi, my name is Weiliang Ma, and I will be talking about the work that we did at Huarong University of Science and Technology about a GPU-accelerated zero-knowledge proof system. Zero-knowledge proof is a cryptographic protocol that allows one party to prove the correctness of a statement to another party without revealing any information beyond the correctness of a statement itself. It can be adopted in a variety of privacy-preserving applications. However, a significant obstacle in using ZKP is the performance overhead of its proof generation. In a typical anonymous transaction workload, the proof will need half a minute to generate one proof, while the verifier only takes a few milliseconds to verify. So we want faster prover to make ZKP truly useful. There are 2 most time-consuming computations in proof generation. For number-theoretic transform computation, recent works rely on extensive data shuffling to ensure contiguous memory accesses, and the underlying library to support large integer is not optimized. For multi-scalar multiplication computation, they have not explored the opportunities of eliminating redundant computations, and they cannot effectively handle the load imbalance caused by the sparse data distribution. To achieve our goal, we developed GZKP that supports different levels of security requirements and brings significant speed up. For more information, please attend my talk in session 7 at 10:20 a.m. on Wednesday.